Alright, so we're going to be looking at factoring out a GCF, and we've already looked at factoring, but I want to look at something that we should always check for. Before we start factoring, we need to see if there's something that all of these terms have in common. This is going to make our job easier in the long run. And if I tried to factor this trinomial here just like it is, I'd be saying, okay, what's A times C? And I'd be multiplying 5 times 80 and getting this big number. So what I want to do before I start factoring is look for something all three terms have in common. In this case, every single one of these terms can be divisible by 5. They all have 5 in common. So what I'm doing is I'm factoring out a GCF. And that's going to give me easier numbers to deal with when I start doing the AC method and I start factoring. So I divide all of these by 5, and that's going to give me an easier trinomial to factor because these are now smaller numbers. Okay, so now I'm factoring with numbers that multiply to 16 but would also add to 10. So we always want to check for that, make sure that we factor out something that they have in common. Now I would still factor this pretty much exactly how I did, but I want to make sure when I do factor and I factor out a GCF, this 5 doesn't get forgotten about. This 5 that I factored out, it was something they all had in common. It's going to be included in my answer. Okay, so when I get the factors and I do the AC method like we talked about, you know, what are factors of 16? If I were to factor this, what multiplies to 16 but adds to 10? Those are the numbers that I would be looking for if I factored this trinomial here. Well, what multiplies to 16 that adds a 10? And that would be 8 times 2, because 8 times 2 gives me 10, and 8 times 2 gives me 16, and 8 plus 2 gives me 10. So those are my factors, and I would write them out just like we've been doing. N plus 8, N plus 2. But I've got to include what I factored out in the very beginning. I took out a 5. Don't forget that when you're looking for the correct answer, because there's the 5 I factored out, and these are the other two factors. I wonder, when I say factors, these two factors would have to multiply to give me what I started with up here in the top. Now that won't work if I leave out the 5 over here. So we have to make sure we include the factor that we factored out in our final answer. Okay. Now those all had a 5 in common, but you're going to sometimes see trinomials that don't just have numbers in common. For example, these all have a 3 in common. Okay, but you'll notice it's not r squared up here in the front, it's r to the third power. Well, and this one's r squared, and this one here is r. So they can also have a variable in common. So every single term in this quadratic has an r and a 3 in common, and it is possible that they can have more than just a number in common. You know, everything can be divided by 3. Well, I can also divide an r out of every single one of those, and that would give me something that can actually be factored, because as it sits, you can't do the AC method if the variable r has a is being raised to the third power. It has to be squared for me to even be able to factor this. So I would have to factor out the r that they have in common, and that would give me something like this, r squared, because this r up here and the r on bottom, one of those is going to cancel each other out. So the reason that gives me r squared is because if you remember, r to the third power right here is really r times r times r. If you divide it by r, one of those is going to cancel out. So I'm going to be left with r squared. Here, one of the r's down here cancels out one of the r's up here, and I'm just left with 2r. And then down here, the r's just completely cancel out, and I'm left with -8. So now I have something that can be factored, because now it's r squared. But just like before, don't forget that this 3r right here is also going to be included in my final answer. When I do factor this, I had a 3r that I factored out, and then I'm going to, of course, have the two factors that multiply to -8 and add to +2. So don't forget the GCF that you factored out. Here the GCF was 3r. So whatever they have in common, that's what I'm looking for. And that's what I'm always going to check for. Always look at the, if you didn't catch it, it would just make the numbers bigger and harder to deal with. Now you could still factor them, but it's always check for a GCF before I start trying to factor anything. That's one of the first things I'm going to look for is a GCF. Now you're going to see binomials. Now usually we're used to seeing an A term, a B term, and a C term over here. This is what a little different because there is like nothing over here. There's not a C term, so we would say that 0 is technically the C term in this. Now the good news is if you ever have two terms and it's just an A and a B, I can factor out a GCF, and that's actually all I have to do. As long as the first term is the A and the B. Now we're going to look at some where there's an A and a C, but this one we know that's an A term because it's A squared, and I know this is a B term because it actually has this little variable n beside it. So I know that those are A and B terms, but what do they have in common? Well, 2 goes into 6, 2 goes into 10. They have a 2 in common, and this one has n squared and this one has n. So they both have n, at least one n that they have in common. And when I factor that out, my new trinomial here, 6 divided by 2 gives me 3, n squared divided by n gives me n, and then negative 10 divided by 2 is negative 5, and then the n's just cancel out. Once I get it to this point, now I can't factor that. 3n minus 5, I can't do anything else. That's not n squared. I can't do the AC method. I don't have to do that. So if you ever see just an A and a B, all you have to do is factor out the GCF and you're done. This is my two factors here that multiply to give me what I started with. So you don't have to go any further. If it's just an A and a B, factor out the GCF and that's it. Okay? And now there's another special case we want to look out for, and this is called a difference of squares. And what I mean by that is I have a difference of something, and if you understand what a difference is, a difference just means subtract. Okay, so I have a difference, these are being subtracted, and when I say squares, I'm talking about perfect squares, and that goes back to those numbers like 4 that we know. Well, that 4, if I said what's the square root of 4, well, the square root of 4 is 2. 4 is a perfect square, and there's a lot of numbers that are perfect squares, you know, 4, 9, 16. These are all perfect squares. 25, there's some pretty common ones, and the reason those are perfect squares is if you remember, you know, these are the result of 2 times 2, 3 times 3, 4 times 4, and so on. Those are perfect squares, and of course I always forget about the smallest perfect square. 1 times 1 gives me 1, and people always forget about that one. But these are all perfect squares because they're the result of two numbers, equal numbers, that multiply to give me that result. So 5 times 5 is 25. That means this is a perfect square. 4 times 4 gives me 16. It's a perfect square. So if you ever see something over here, this number here, if it's an A term and a C term and it's being subtracted, the only way that that's going to work is if those two numbers, those two terms are perfect squares. So r squared, that's a perfect square because r squared is the result of r times r. Just like 4 is the result of 2 times 2. That's a perfect square. And 9, this is a perfect square because 9 is the result of 3 times 3. So that's a special case we want to look out for. If you see two terms, now they don't have anything in common, I can't factor anything out of those two terms, but if you look at that, it is a difference, they're being subtracted, and it is two terms that are perfect squares. So I'm not going to have to do the AC method on this. I mean, I could technically do the AC method and it would still work, but I don't have to. If these are both perfect squares and they're both being subtracted, I'm just going to take the square root of each side. The square root of r squared is just r. The square root of 9 is 3. And I'm going to have two factors here. I'm going to have a r plus 3. And I'm going to have an r minus 3, because when we're dealing with perfect squares, the square root of 9 is essentially 3 because it is 3 times 3. But you could also have the square root of 9 be a negative 3 because negative 3 times negative 3 gives me positive 9. So I'm going to always get two factors out of this. When I have a difference of squares, I'm always going to get the square root of each of those terms. R squared, the square root of that is R. The square root of 9 is 3. I'm going to get a positive and a negative version of that, and that's been factored. Okay, now I could have done this the old-fashioned way, and I could have done it the AC method and said, okay, well, what is my A term here? My A term is 1. What is my B term? Well, there's not 1, so technically 0, but I do have a C term. So if we did the AC method, I'd say, okay, well, what multiplies to negative 9 but adds to the B term? Well, there's nothing in the middle of this. There is no B term, so what does that mean? Well, it just means that there is 0. There's no value there. So if I was looking for numbers that multiply to negative 9 and add to 0, the only way for that to work is if those two numbers have different signs and they have to be equal. Otherwise, they have to be of the same value, an absolute value. 3 and negative 3. If I were to add those together, they give me 0. If I multiply them, they give me negative 9. And the only way that that can work is if these are perfect squares, because if there's not two equal numbers like 3 and 3 that multiply to give you 9, it's not going to work. I couldn't do this with anything else unless this number here is a perfect square and this number here is a perfect square. You know, you factor that. If you did the AC method, you're still going to get the same answer. It's still going to be, R plus 3, R minus 3, just like when we realized that it was a difference of squares. We can do it either way. You're still going to get the same answer. But if you ever see two terms that are perfect squares and it's a difference of perfect squares, or I can always take that little shortcut. I don't have to do the AC method. For example, here I've got a perfect square here, a perfect square here. They're being subtracted. What's the square root of each side? Well, the square root of 4 is 2. The square root of n squared is n. And then I look over here at 25. Well, what's the square root of 25? The square root of 25 is 5. I'm going to have a positive version of this, and I'm going to have a negative version of this. And that is already factored. I don't have to do the AC method. I could do the AC method if I wanted to, but I don't have to. So I'm just looking at, are they perfect squares? Are they being subtracted? And that's it. This would be my final answer. No need to do anything else. Just find the square root of each side. You're going to have a positive and a negative version of those square roots.